All right, today we're looking at this idea of a series. Right here, a series. We're going to look at both arithmetic and geometric series together. First, I'm going to define what a series is, and then I'm going to show you the types of problems that you'll have with this. So first, a series. When the terms of a sequence are added together, the resulting expression is a series. So if we have the pattern 2, 4, 6, 8, and so on, this would be considered a sequence. But when we try to add it together, it would be considered a series, like you can see right up here. These would be the series when we try to add the terms. Now, like it says here also, a series can be finite or infinite. So there are two different types of series. A finite, where you can see it's literally just whatever these four numbers add up to be. Or it could be an infinite series, meaning we're going to say what the entire thing, if it were to go forever and ever and ever, what the entire thing would add up to. So a series is adding all the terms of a sequence. We have two types. We have a finite or we have an infinite series. Now you're going to see sigma. You're going to see summation notation. If we wanted to say, we have that series from earlier, 2, 4, 6, 8. If we wanted to say to add all of these together, we would write, we want to take the sum from the first term to the fourth term, and this is the explicit formula of it, 2i. That would be this is arithmetic, we're adding 2 each time. This would be the explicit formula for it. So this would be another way to say, this would be using summation notation, to say take the sum of this sequence from 1 up to 4. So we'd have to write the explicit form first. Notice they use I. I'm not super picky about what variable you use. I even switch it up. So if you use n, as long as those two are the same, then you're fine. If they said we wanted to take the sum of an infinite series, we would say, okay, we want the sum from 1 to the ... to infinity of the explicit formula for that pattern. So that might seem kind of confusing. Hopefully that's not too bad, but we'll look at some examples where we use this. Write the series using summation notation. So first we have to figure out, is this arithmetic or geometric? Well, this we are adding 3 every time, so it's arithmetic. My explicit formula for an arithmetic sequence looks like this. My first term is 1. My common difference is 3. And I would expect you to simplify this then, to distribute 3n minus 2. Now, if they want me to write this using summation notation, then I would say, okay, I want the sum, and I'll use n just to show you can use a different variable. From 1, this is 1, 2, 3, 4, 5, from the first term up to the fifth of 3n minus 2. That would be writing this same series in summation notation. If I look at this next one, I have to again figure out if it's arithmetic or geometric. This is changing by 3, this is changing by 7.5, so it's definitely not arithmetic. If I do my second term divided by my first, this would give me 2.5. So here's my R value, my common ratio. I want to find the sum. This is my first term. I'll use I this time from 1, and I've got the ... So from 1 to infinity of, well, this is a geometric, like we said, so we have a sub n equals a sub 1 times r to the n minus 1. My first term is 2. My common ratio is 2.5 to the n minus 1. So if you look at what we've done here, we said, okay, here's what a series is. A series is just a sequence, but we're adding all the terms together. It could be finite, where we know what all of them are, or it could be infinite, where it keeps going forever and ever. We have this thing called summation notation, where instead of just writing that we're adding all these together, we could write it in a little nicer, cleaner form using sigma, which is kind of awesome. So what we looked at in this first example then is how we would write a series, both and if it were arithmetic or if it were geometric, using summation notation. They gave us The longer form of it, we wrote it in summation notation. This slide will be something that you want to have written down. You'll be able to use this on your quiz. I'll give this to you on your test as well. But these are the formulas that we have looked at so far. So you can see arithmetic, we have the sequence formula, and geometric, we have the sequence. I use G, doesn't really matter that much. You could use G or A or whatever. Now in this next line, you've got the series formulas, meaning the sum. The sum of a, and these would have to be finite. The sum of a finite, this one's finite too, of a arithmetic series is n, meaning the number of terms, parentheses, our first term plus whatever our last term is. If we want the sum up to 50, we'd have to plug 50 into our equation and find the 50th term. Divided by 2. Here at geometric, it'd be our first term, 1 minus our common ratio to the n, which n is, again, our number of terms, over 1 minus n. Again, this would have to be a finite. We can find the sum of an infinite, and this is a little thing. This would be the formula, this is why it's written on the bottom. For an infinite geometric sequence, or infinite geometric series, but it has to be decay, meaning r has to be less than 1. So we can only find the sum of one infinite thing, and it's an infinite geometric if the sum, or if it's going down, if r is less than 1. Okay, these are going to be important. For your quiz, I'll probably just print these off, and then Miss Jen will hand you one of these with your quiz. So you'll have it just right in front of you. So if we were asked to find the sum here, I've only got 2 more examples and you're good. If we were asked to find the sum here, we would first need to identify, is this geometric or arithmetic? Well, if we look at this form, we don't have any exponents, so this would be arithmetic. So that means I'm using the sum equals n times a sub 1 plus a sub n over 2. N is my number of terms. That would just be 20. I'm finding the sum from 1 to 20. My first term would be if I plug 1 in, so 3 times 1 plus 7 would give me 10. A sub n would be the last term that I have, which is 20. So 3 times 20 plus 7. 3 times 20 is 60. No, it is not. Of course it is. 60 plus 7 is 67. Out of all the things the last couple weeks that I have not missed, hearing 6, 7 is probably at the top of it. Okay, so then we have to do, and I'm just going to type this whole thing in my calculator with the parentheses and everything. So 20 times 10 plus 67 over 2 would give me a sum of 770. Sorry, I'm just double checking. Perfect. Let's look at another example. Here, this one is geometric. So if I'm looking at my table, a geometric, it's a series. I'm finding the sum. Here would be my formula. So it is S sub n equals G sub 1. And I always forget, do they put the 1 first or the R? It's 1. Over 1 minus R to the n over 1 minus R. So first I need to find my first term, meaning I need to plug 1 in for K. That would just give me 4. My R, my common ratio, is 3. My number of terms is 10. Again, I'm just going to plug this right into my calculator. 4 times 1 minus 3 to the 10th power over 1 minus 3. This gave me 100 18,096 would be the sum. Again, this were to say if I plug 1 into this, get the value, plus 2, get the value, plus 3, get the value, 4, and so on all the way up to 10. It's adding all of those things together. Okay, now you're going to move on to the next worksheet in your packet, which is arithmetic/geometric series.